Hello everybody, this is Jason Wang from Red Hat. Welcome to the K1 forum. Today I will give a talk about how VDPA is supported in the Linux kernel. Here is the outline. We will first go through the virtual architecture, and then we will try to introduce a new type of device called VDPA device. And after that, we will discuss the design and implementations of the VDPA framework in the Linux kernel. And we will conclude the presentation and will be a Q&A session. So here is the virtual architecture overview. So you can see that the virtual architecture could be split into 3 layers. In the upper layers, virtual defines several different types of device. For example, it could be networking device, SCSI device, block device, etc. In the middle is the core device model, which could be split into the definitions of the word queues, feature bits, and config space. And on the lower layer is defined several transport, which ties to device type to an actual bus. So the spec defines PCI transport, MML, and CCW transport. So several different types of virtual devices has been implemented in software. The first device implementation is done in QML, but its performance cannot satisfy our requirement. Then they move the data plane to the kernel by using vhost protocol. It can do better than QML, but it's still not sufficient. So we offload the data plane from QML to another dedicated remote process through the vhost user protocol. Then it can achieve the best performance that a software data plane can even achieve. So with the virtual specifications and the software implementations of virtual device, we get good application usability. We get a unified device interface forecast, and we even get live migration support. But there are still several drawbacks. The first is that the software implementations requires extra CPU cycles to be spent, and it requires extra management costs for settings such as CPU or memory affinity. And the last and probably most important one is that it can't reach the wire speed due to the software overhead. Consider the community high-speed Ethernet network card become available. In order to address all the limitations found in the software virtual implementations, some hardware vendors start to implement a hardware implementation for virtual, which means the device is fully compatible in both control paths and data paths with the virtual specification. Then it could reach wire speed, and there will be no CPU overhead, since all the data plane has been uploaded to the hardware. The unified API was preserved, and there will be no vendor lock. But there are several issues of hardware virtual implementation. The first issue is that the current virtual is not designed to be virtualized. There's no API for save and restore device state in the current virtual specification. This means if you just expose raw virtual device to the guest, it can't be live migrated. The second issue is that virtual is thin and simple, which means it will be hard to be integrated with the existing hardware stack. So modern real hardware is much more complicated. For example, the SRV capable Ethernet card usually have an embedded switch. This means the vendor may have their own specific API to configure to program the switch. All of this API was missing in the virtual specification. And to be fully compatible in the control path also means a redesign of the control path, which tends to be a challenge. And it will be very hard to add vendor-specific values, which usually requires vendor-specific extensions. And the manageability is also bad, since there's no management API defined in the virtual specification. So in order to address all the limitations we found in the hardware virtual implementations, we introduced the concept of VDPA. So what is VDPA? It's short for vhost datapath accelerations originally, but then we realized vhost is just a cancel virtual datapath offload. So we changed the definitions to the virtual datapath acceleration. VDPA device is basically a kind of hardware that has a virtual compatible datapath, which is defined by virtual spec, but it allows a vendor-specific control path. And it was required that such control paths should be functional equivalent or superset of the virtual control paths defined in the spec. In order to support live migrations, the VDPA is also required to have part of the vhost features, such as device recovery or dirty page tracking. Note that the dirty page tracking is not a must. So from hardware perspective, VDPA device is a functional superset of the virtual device. So it contains the virtues, the virtual features, vhost features, and vendor-specific config method, which is functional equivalent to the virtual config access. And beyond that, it was allowed to add vendor-specific features on top. So why we need VDPA? You can see that we gain almost every advantage of the hardware virtual implementations. For example, it has a unified data path with open standard, and it can reach wire speed. Besides those advantages, we also gain more. So we gain live migration support by supporting the host features like device state recovery. It was also allowed vendor to add their add-on features on top. But if we just expose raw VDPA device to the software, there could be still several gaps for the end-to-end delivery. For example, do we really want to expose all the complexity and difference of the raw VDPA device to the app layer? Or do we want to integrate the VDPA device with the existing systems, or we revamp the view for a new dedicated subsystems? And also, how about manageability? Is there a vendor-specific manage API, or it could be a unified one? And how about heavyweight drivers or lightweight drivers? So in order to answer all of those questions or these comments, we want to introduce the VDPA kernel framework. The main goal is to bridge the usability and the manageability gap with the raw VDPA device. So it's basically a framework with the following features that is required. First, it should hide the complexity and difference of the underlayer device and present a simple same device API to the software. And it also try to present a unified management API to simplify the task for the upper layer stack. And it will try its best to be integrated seamlessly with all the existing subsystems, which means it will try its best to reuse the codes in both kernel and user space applications. And this framework should not be designed for user space drivers only. It should serve for both kernel and user space drivers. And the framework should be designed to be bus or device agnostic, which means it will allow any types of device, such as non-PCI device, FPGA device, or even software emulated device. And it will try to keep the drivers as lightweight as possible. So here's the overview of the VDPA framework. So you can see that on the hardware level, there could be several types of VDPA device, which is all connected to the VDPA framework. And to the app layers, it can choose to connect the VDPA device to both vhost systems and virtual drivers. So when connected to the vhost subsystems, it will present a vhost device and let applications to use a vhost U API to control the device as if it was a vhost device. And when connected to the virtual drivers, a kernel visible virtual interface will present to the kernel I/O subsystems. So the applications can choose any of the mature uAPI supported by the kernel are subsystems to control the vhost device, the VDP device as if they were virtual device. And the framework will also try to present a unified management API for the management applications. So as discussed, the framework is trying to allow several different types of device and different types of drivers. So it's natural to consider to introduce the bus. So the VDP bus is the core concept for the VDP framework for abstracting the hardware, which allows different VDP device and drivers to be attached. And the VDP bus also defines the communication protocol between the bus driver and the device. So those communication protocol is a set of callbacks, which is called VDP config operations. And VDP device is the device abstractions provided by the VDP parent device driver, which have several common attributes of the VDP device and also the implementation of the VDP config operations. So on top of the VDP bus, several different types of VDP bus drivers were allowed to be attached. Those tasks is to connect the VDP device to the existing kernel subsystems and use the VDP config operations to talk with the VDP device. So you can see from the view of the VDP bus driver, it can only see the VDP device and VDP config operations. All the complexity and difference was hidden via the VDP device abstraction and bus. So VDP device is for the common abstractions, and VDP parent is the module that provides such abstractions. So it needs to provide the common attributes and to implement the config operations of the VDP bus. So the config operations usually contain several different types. For example, it will contain the virtual specific operations such as the virtue attribute setting, the device state, feature negotiation, and something, etc. Yeah, and it will also contain the interrupt and the doorbell acceleration method for fast access to the interrupt and doorbell. And in order to be more generic, it will also contain the DMA map and unmap method, which could be very convenient for the device that has on-chip MMU or have a sophisticated DMA mapping logic. And it will also contain the vhost operations for device state recovery and dirty page tracking. So the parent can be any type. For example, it could be a real parent device driver that talks to the VDP device directly, or it could be an intermediate layer on top of another device driver framework, or it could be even a software emulated VDP device, or a proxy or relay of the VDP protocol to some other modules or even user space. So we allow several different types of VDP bus drivers to be attached. So we will first talk the vhost-VDPA bus driver. So this bus driver is used to present a vhost device to the vhost subsystems. So it serves mainly for the user space virtual drivers. For example, it could serve for QMO vhost backend, for QMO to present a virtual data path to VM, or it could serve for the DPDK virtual PMD, which serves for NFV use case. So the idea is trying to reuse as much vhost generic UPI as possible for the data path setting. But it also requires some dedicated uAPI extensions for full device abstractions, which is missed in the generic vhost uAPI. So those UAPI usually contains something like configure space access, state, device state get and set, config interrupt, etc. So the traditional vhost user applications only need very minimal changes. Then it can use the vhost VDPA bus drivers to control the VDP device as if they were virtual device. The second bus driver we provide is the virtio-VDPA bus driver. So its goal is to present a vhost device to the virtual bus. Then this pseudo or proxy virtual device could be probed by the virtual drivers. So the virtual device will be visible to the kernel I/O subsystems. This is done by introduce a new VDPA transport for the virtual bus. Then the kernel I/O subsystems can use VDPA device as if they were virtual device. This means the applications can use, for example, TCP/IP stack, storage stack, IO XCP, or any kernel I/O systems to transfer data between itself and the VDPA device. The main use case for the virtual-VDPA device is for bare metal applications or containerized applications. And for the management API, we will try to introduce a dedicated VDPA-specific Netlink protocol for the VDPA device management, which mainly contains the first is lifecycle management to create, destroy, enable, disable, and also to setting the attributes or provision the VDPA device. The idea is to introduce a new VDPA programs that will be integrated into IP route 2. And then the management API will use either these programs or the Netlink protocol directly for a unified configuration interface. All VDPA device, parent device is required to implement the VDPA Netlink protocol. So currently Linux kernel have supported 3 VDPA parents. The first is the Intel FCVF. So from the hardware perspective, it addresses a virtual device plus Intel specific extensions. And the VDPA is implemented through a dedicated VF. So its parent driver is simply a PCI VF device driver. The second VDPA parent is the Manlox 5 VDPA parent. So this device is also implemented in a dedicated VF, but it has a total vendor-specific control path. Its parent is an intermediate layer on top of the existing Manlox 5 core module. And the third parent is the VDPA simulator, which is basically used for device testing, feature prototyping, etc. So this parent is implemented purely through software emulation. And we are working with vendors for more types of VDP parents, such as the ADI, which complies the Intel Scalable LV specification, or device or vendor-specific device slice such as subfunction, or even a PCIe endpoint device, which means the VDP is implemented via a remote SoC. So here's basically the status of the VDP support in the current Linux kernel. So basic functions such as VDP core, bus drivers, and 3 VDP parents has been merged. And the basic QML function has been merged by QML. And then we are working on, for example, the Netlink-based management API, which would be posted soon. And the live migration support is also under development. For live migration, we will probably start from a software-assisted live migration first. This means it doesn't require any device support for dirty page tracking. QML will try to assist the device for dirty page tracking. And after this, we will try to invent new API for supporting dirty page tracking from the hardware. And you can see also the controlled queue work is being developed upstream. And we are working with vendors to make sure that the framework and the drivers can work for device other than networking. We will probably start from the block device. And for the future, there are several things in our mind. The first is we will need to finalize the documentations in the kernel source, which contains both the VDPA device API definitions and the vhost-VDPA API. And we also plan to cooperate with the platform vendors to support shared virtual address or even virtual shadow address. And we also plan to extend virtual specifications for some VDPA specific extension. Okay, so let's conclude these presentations. First, we introduce a new type of device called VDPA device. The VDPA device has virtual data paths with vendor-specific control paths and vhost features. And we introduced the vhost framework in the Linux kernel, which tries to hide the difference and complexity of different types of VDPA device and present a unified device and management API to the upper layer. The VDPA framework contains the VDPA bus and a device for abstracting the device. And we also allow different types of VDPA bus drivers for connecting the VDPA device to various kernel subsystems. So we support both vhost and virtual drivers to let the VDPA device be used by both the kernel virtual drivers and userspace virtual drivers. With the help of both VDPA device and VDPA framework, we could achieve wire speed virtual with the best usability and manageability. So there will be no vendor lock, and there will be left migration support or even cross-vendor left migration. A unified management interface was provided for ease the task of the management stack, and we will get material software stack in both host and guest, since we present virtual or vhost device to the upper layer. So here are some good references. First is the presentation done by Steve in the previous KVM forum. And the second is 2 series of blog wrote by us, which contains almost every aspect of both virtual and VDPA. And it also contains several deep dives for the VDPA kernel framework and its the typical use case. So you are welcome to go through those blog series and give us feedback. And it's also be useful for review and have a look at virtual specification. And if you want to ask or hear from what is recently being developed for VDPA aspect, you are welcome to subscribe the VDPA development mailing list. So VDPA is come to real life. It's not a concept in the paper. You are welcome to consider to deployment the VDPA device in your cloud, or you want VDPA-based hardware. And you are also welcome to test and contribute to the VDPA framework. Please contact us if you have any questions. For example, the hardware design, driver implementation, deploy, integration, and management issues, or even feature requests. You can drop a mail to either the virtual networking mailing list or a private mail to me. That's it. Thanks.